linearly independent set of vectors. Could you guess what we need in order to talk about a linearly independent set of vectors? Yeah, so let's let m and n be part of the natural numbers, and let's let a1, a2, all the way down to an be an element of Rm. We say the set a1 to an is, what do we say? Not linearly dependent. In other words, linearly independent. That's maybe the ugliest looking P that I've written in a long time. Okay. And underneath that, let's literally think to ourselves, not linearly linearly independent means what? Not linearly dependent. And what does that mean? If and only if, well, we could go with that definition, but we just came up with a much, much better way to state linear dependence. What's the way to state linear dependence without having to work with a clunky definition that you have to isolate one of them a priori before you've investigated? There's a way, if a set of vectors is linearly dependent, there's a way to create the zero vector by taking non-zero linear combinations. What would it mean then for a set of vectors to be linearly independent? You can't get zero unless you take all zeros. If and only if, the only way to produce a zero vector is with x1 equal x2 equal xn equal 0. Okay, and another way to say that is that if we take x1 a1 plus x2 a2 plus xn an, and we set that entire thing equal to the 0 vector in m by 1, how did I know that that was supposed to be the m by 1 0 vector? What do I know about each of these vectors to begin with? They're all m by 1, which means that these vector additions are m by 1. These scalar additions pop out in, scalar multiplications pop out in m by 1, so that the linear combination must be, yeah. When is it true that a set of vectors is linearly independent? What must be true about that? It's not linearly dependent, which means that if I produce a zero vector via linear combination, what can you immediately conclude? Yep. The only way to do that is if all the scalars are set to 0.